Hi guys, we are back and today we're going to talk about the definition of a fluid. So the objectives of this lecture is to define what a fluid is, and we'll do it in a couple of different ways. We're going to look at what a fluid is within the solid liquid gas phase diagram or phase ideas. Basically, a fluid is any liquid or gas. And then we're going to discuss the various phases of matter in the micro phase, micro scale, and the macro scale, and we'll discuss characteristics of each. So what is a fluid? And often this is the first question I ask any class dealing with fluid mechanics, and I get a lot of answers. I usually get one about a fluid is a gas that fills its volume, or it can be poured, or it can't support shear stress and all of those sorts of things, and those are all very good descriptions of what a fluid is. I want to dive down a little deeper though and talk about it. I'm showing you a couple of video images here of two fluids, a liquid on the left and a gas on the right, and this is the liquid, and it initially started off with the liquid being poured, and now it's showing you the various laminar and turbulent profiles, and we're back to the turbulent profile of a liquid emitting from a pipe. And the film on the right is a short film showing a gas behavior. It's actually a combusting gas, and it's a beautiful set of images related to gas flow. But to get down to really understand the differences between a solid, liquid, and a gas, and fluid behavior, we really have to go down, I think, to the basics, all the way down to the molecular level. So before we do that, we'll talk about the three sorts of levels. Down here at the bottom is kind of the quantum level, and then as we move up, we might talk about molecular or microscale. So in a quantum, we're talking about the vibrations of individual atoms and how they store energy, including maybe electronic shell behavior. As we move up to microscale, this is individual atoms interacting with each other via parapotentials such as van der Waals forces and collisions and translational energy. And then finally, when we get up to microscale, all of that is put together under what's called the continuum assumption, and we just assume that the fluid has some behavior. So we'll cover kind of all of that over this lecture and the next one moving forward. And I don't want to spend a lot of time on it. There's whole classes obviously taught on quantum mechanics or statistical thermodynamics and molecular behavior, but it is kind of nice to put the context of what we're doing here in advanced fluids within this larger structure. So here at the microscale is an image of what a gas and a liquid and a solid look like. And it'd be nice if you could just pause the video for a moment and think about each one of these. When I teach this class, I usually ask students to write down two characteristics of each phase. So just spend a minute to do that, and when you're done, just restart the video and I'll show you some of my examples. All right, so here's some properties of each one of those. With a gas, we usually think of a gas as having wide separation of atoms or molecules, such that the bulk of their internal energy is stored within the translational motion of the atoms. And there is little parapotential interaction between them. So in a perfect gas behavior, such as argon, that valence shells are full, there is no potential between them. They really interact just with collision behavior, and that's where the original foundation of kinetic gas theory started, and that's where the ideal gas equation comes from. Any sort of attractive forces that can exist between molecular gases is a deviation from non-ideal behavior. Within a liquid, you still have this large volume, and you still have molecules that move through this volume and have a lot of translational energy, but they also contain, they also have parapotential energy between them, so they tend to attract or repel each other, and in so doing, it tends to keep the molecular structure confined. So liquids, as a result of this pair interaction or this attractive forces between them, they form liquid-solid surfaces, but they're still able to deform and take the shape of their containers. So the intermolecular forces are not strong enough to bond the material together, so to speak. That's when we get down to the solid. When you get down to the solid behavior, the intermolecular forces between the atoms or the molecules are strong enough to bond these materials together in a lattice structure, so they no longer have translational energy, but all the energy is confined to vibrational energy within the lattice structure. So strong intermolecular forces between neighboring molecules and result in a rigid solid structure. So I think this is a helpful way to think about how what we see and what we think about as a liquid gas characteristics come about if we think about the molecular structure. Where does the energy go in a molecular structure? As I mentioned just briefly, into translational motion, vibrational motion of the molecule or atom, rotations within of that atom, and then electronic energies within the atom. So electrons can jump up into higher valence shells and then come back down. So this is a molecular dynamics simulation showing the hydrolysis of amorphous silica. So this is showing a water molecule here interacting with this bonded glass structure. And you can see that it has, via the van der Waals forces, bonded itself. Now it has actually broken that oxygen bond and reformed with the two hydrogens. So what did you see in this simulation? Maybe take a minute to think about that and restart the video. Basically, all of the bonds were connected bonds with the molecular structure, and there was little translational energy within the molecular bond structure. Really just the water had the translational energy here. And the molecules do vibrate. That's where most of the energy is stored. So here's a liquid. This is ice. You can see it's forming the very initial beautiful sort of snowflake-like structure, and then as this ice melts, it turns into kind of an amorphous structure. And you can see the molecules are rolling over each other and beginning to vibrate more, so they're taking on more and more translational and vibrational energy. This is as it is heated up, right? And so we can see this increase in energy, and eventually it just turns into kind of a gas, right? Where there's lots of translational energy and there's a wide separation of each molecule. So the pair potential, the attractive repulsive forces between them are minimized compared to the vibrational translational energy. What did you see in this video? Well, the molecules are initially aligned in a very ordered way, like in a lattice-like structure. There's lots of translational motion of the atoms and molecules. Once it melts, it becomes a liquid and then eventually a gas. And the molecules vibrate more in the liquid state as compared to the solid state. As they took on more energy, that energy had to go somewhere. Finally, we're going to look at just a quick MD simulation of an argon gas. Again, as it is heated and its total energy is increased, you can see that basically it's all translation here. It's just balls in a periodic box just flying through the structure. So argon is nice because it is a perfect noble gas, so there's no electron energy, so it's easier to model an argon gas like a collection of rigid spheres. So what did you see in this video? Lots of translation and vibration initially, known as the hard sphere model, so little potential forces between them. And as the temperature decreased, the translation and vibration was also reduced. All right, so we're really not going to, this class is not going to focus on the molecular dynamics at all, but I thought I'd just give you a brief taste of it because we will at times refer back and forth, especially when we do compressible flows. Oftentimes, a distinguishing factor between solids and liquids and gases is the fact that a solid can support shear stress, static shear stress, so it can support a static load. So if I place a load on a solid, it will deform, as shown here by the dotted lines, but it will not necessarily yield to that static load. However, a liquid always deforms to a static load, as does a gas, so it can't support shear stress. It can support shear stress if it's continuous motion, and we'll talk more about that later, but for a static shear, it can't resist. So if I just took a liquid and I displaced it and stopped, it isn't going to return to its initial position because it doesn't store that shear stress, so to speak. So the equilibrium position here shown with just a volume element or an area element of what the loading condition looks like. On a Moore circle, a solid can support both static shear and normal stress, so both shear and normal stress, and stress also the diagonal of the stress tensor being pressure. Here, the Moore circle of a liquid or a gas is really kind of boring. It's just confined to the x-axis here. The static shear will come into play within a fluid element if there's motion, dynamic motion, then it can support static shear. But we'll get more into that when we talk about the derivation of the Navier-Stokes equations and the extension of Newton's ideas to a full generalized stress tensor. All right, staying on the bulk scale, I think you're used to seeing phase diagrams of various materials, and here's a phase diagram of water. It's a pressure-temperature phase diagram showing the liquid, solid, and vapor phases of water. I think water is kind of unfortunate because it has these extra names like, instead of saying solid water, we typically say ice, or instead of saying liquid water, we typically say water. And then we might say steam, which really is a collection of vapor and liquid. So water has kind of extra baggage associated with it, but really it's just solid, liquid, and gas, right? And water, the word water doesn't imply the phase necessarily, although I think in popular culture it does. You can also have a variety of phases within the solid phase, right? So water, I think, has 13 solid phases that have been discovered at this point. So 13 ways that the molecular structure stacks to make a solid structure. And you're familiar with alpha, beta phases of iron and quartz and that sort of thing. So just to conjure up these things, this is just part of the review. And so I wanted to talk about this word fluid, the name of this class being advanced fluids. Fluid is not a phase, but rather it represents both the liquid and gas phases. So anything we talk about in this class related to liquids, related to a fluid, applies to liquids and gases. We're going to treat them the same at the macro scale. All right, so this is the end of this lecture where we talked about phases of matter and discussed solid, liquids, and gases from a molecular perspective. And then we talked about characteristics of each, and then we talked about the macro scale. Next time we're going to talk about fluid properties at the macro scale and a very important assumption that bridges the gap between the macro and the micro scale, and that is the continuum assumption. All right, so until then, we'll see you next time. All right, bye-bye.